So we're jumping into lines in 2 and 3 dimensions. So this is a bit of a new one, but we're going to look at our vector operation. So if we're considering that we wanted a line of some kind here, what we do in this space is if we can find a fixed point on this line, we can then just come up with a vector that goes in the direction of this line. So we just need some vector B that's parallel. So all we need really is, like, if we get O to A, it gets us to this point here that's on the line. We get a fixed point on the line, and then we add some vector in this direction B. We can pretty much have any point on these lines here. So I've drawn this here, but this R value could actually be anywhere. It could be up here. It's going to go along the line here. So if we were going to build this out, what we would do is we would consider this point R. So this point R over here is the origin to R. That's its position. And so we would go, to get this R vector, we would go along the A vector, and then we would go along this B vector. Now, depending on where the point is, depends on how far along in this direction B we want. So we need this scalar, which we've got lambda here, to sort of put us, it could only be like a tiny bit we want to go along the line to this point, or it could be a lot. And so we end up with this vector equation, which is this vector R, which is going to give us all the points on this line, is going to be equal to some fixed point on this line. So this fixed point is the position vector A, or OA, plus lambda times our direction vector. So let's just label those up. So this is sort of our fixed point. And this is going to be known as our direction vector. So if we consider these particular ones and we wanted to figure out R, I'm just going to say that R is going to be, and I'm using a different, actually no, let's use our, no, I'll match up to the textbook. I'll change it in a minute. So if we have R equals these points X, Y, Z, then we're going to have R, our R vector. We want it to equal our A vector. So this is going to be A1, A2, A3. And it's going to be added to our lambda, our direction vector here, which is going to be B1, B2, B3. So I might even, so this, let's just move, we'll move these just a little bit to the left so I can fit the next bit in. Cool. Okay, so this equals X, Y, and Z. So what this is actually broken up for us is it means that we can consider the individual elements, and we've got this means our X component. If we wanted to find our X position, we just need the X value of our first, our fixed point, plus our direction vector times our scalar here. So these are actually called our parametric equations, and these are really important. So we can break these up into the individual X, Y, and Z into their components, and lambda here is our parameter. Now, it doesn't have to be lambda. Sometimes it can be different letters. Now, our Cartesian equation is always these three things next to each other, and what you'll realise is these all equal lambda. So if I was to, that's a shocking lambda. If I was to rearrange this here, if I think about this initial one, if I was to rearrange it for lambda, it would be X minus A1, and then I'd have to divide B1, and that would equal lambda. So that's just a bit of definition time. Let's jump into this example here. So a line in space passes through this coordinate in the direction 4 plus 5 minus 6. So describe the line using a vector equation. So what we've got here is we've got our vector R is going to be equal to A, our fixed point, plus lambda times our B vector. So this will then become X, Y, Z, and that would equal our fixed point. So let's find our fixed point. So it's up here. It passes through this point, 1, -2, and 3. So we're going to have 1, -2, and 3 plus lambda. And now we need our direction vector, which is 4, 5, and -6. So we've got 4, 5, and -6. Okay, and then we just need to define that lambda here is going to be a real number. Okay, now the parametric equations for this means we break up each individual component. So we're going to have x equals 1 plus 4 lambda. So x equals 1 plus 4 lambda. Y equals -2 plus 5 lambda. And z here equals 3 take 6 lambda. Now, the last one here, it asks for our Cartesian equations. So I'm actually going to bring these over just so we can show how we calculate these. So paste, I'm just going to leave these here. I'm going to erase them in a minute. But you will look at this one here and it's going to be x minus 1. So I've just taken 1 from both sides over 4, which is the coefficient here of lambda. And that's going to equal y plus 2 divided by 5. And then our last one here, I'm running out of room, so I'm going to clear this. Let's delete that. So my last one here is going to be z take 3, and then z take 3 over -6. Okay. And we are all solved there. So let's just jump on to the next part because this is pretty quick. So when determining the equation of the line, there are lots of equations that give the same line. So we have non-unique solutions. You can come up with a lot. And we find that in this following example. So find the parametric equations for the line A2, -1, 4 and B1, 0, 2. So if I consider these 2 points, A and B, we're looking at a line that goes through both of them. So in this space here, A to B equals OB, the position of B, minus OA, which equals -1 take 2, 0 take -1, and 4 and 2 take 4. So if we're going to go from A to B, we're going to go -3 plus 1, and then 2 take 4 is -2, and down by 2. Now, the thing is, the direction could also be B to A here. So these particular examples, B to A is going to give us OA minus OB, which would equal, OA was 2, I'm just going to get lazy here, 2, -1 and 4, and B is, so take -1, take 0, and then 4, take 2. Yep, and so this is going to equal 3, -1, and 2. Now, if we knew this was actually a bit long-winded. Realistically, the moment we knew one, we could have done the other. You should notice that these are scalar. These are multiplied -1 by themselves. But now if we consider the 2 lines here, we have, let's consider for a minute, let's just drag this down, copy So I'm going to do 2. So the first one, let's consider doing the line. So our first one here, I'm going to use a navy instead. We're going to do our origin here, and we're going to go O to A, and then A to B. Okay, and this is going to give us the point R on this line. So we would have here R equals OA plus lambda A to B, some variation of this. So this particular one here, our A coordinate is going to be, I'm going back to the textbook notation just for room. So we have 2, -1, and 4 plus lambda, and this vector we did previously. So we've got here -3, 1, and -2. Okay, now I'm just going to break this into X, Y, and Z just so we can do it. Or the other option is, just so you can consider it, we could have gone to this fixed point here. So we could have had, now I'm going to, this is just a second one. Maybe I'll call this R1 and this one here R2. This one here could be OB, and it gets to this fixed point here. And then we can come back this way by, now I'm just going to use a different scalar. We're going to come to our point R, but this one is, we're going to use mu instead as a multiplier. So this would be plus some scalar B to A. Now this means here we're still going to have X, Y, and Z, because that's going to give us our original things. And now we've got point B, which is -1, 0, and 2. So -1, 0, and 2. And then plus mu equals, what do we got? B to A. So B to A is this vector here. So 3, -1, and 2. Now the question actually asked us to find parametric equations. So we haven't found them yet. We've found the vector equation. So we need to specify here. So I'm going to have to just move this down a touch so we can fit. Okay, so this here, let's change back to light blue. Our parametric equations here are going to be X equals 2 plus lambda, 2 take 3 lambda. Y is going to equal -1 plus lambda. And Z here equals 4 take 2 lambda. Okay, this one down here, the parametric equations, are going to be X equals -1 plus 3 mu. Okay, Y equals 0 take mu, -1 mu, and then Z here is going to equal 2 plus 2 mu. So these parameters are different, and you can't use the same parameter. You've got to be careful if you're doing the same line, because those parameters aren't the same thing. We can get to the same point. We could actually make these equal, but we've just got to make sure we have those different lines. All right, thanks guys.